Warm welcome for Florian Haenel from LG Electronics. I keep the pace, so I'll let you know if you run out of time. Otherwise, I just give you the stage.
I think I'll
thank you.
Start a stopwatch. Okay, so I'm Florian. I'm from LG Electronics, senior software engineer, and this is a talk about the WebOS QtWayland Compositor. Now, you might ask yourself, why do I care about the WebOS Compositor? So this should inspire you that you can also ship Wayland in your device. And so it's also a little, tales from the trenches maybe, or lessons learned. So to inspire you to also ship Wayland. I'll introduce myself. I studied computer science in Erlangen. I have 13-ish years of Linux and C++ experience. 8 years I worked with Qt on the desktop. I worked on Migo browser and WebOS. And for 5 years I worked on WebOS.
Ganz kurz, der Wartknopf knistert.
Okay. Thanks. And on WebOS, I worked on the Compositor, hence this talk, also the system UI, and why that is you will learn, and most recently on some of the WebOS apps. So HP WebOS, you might remember, it's a Linux-based operating system. It's web-centric, so we have HTML apps and native apps. HTML apps as first-class citizens, and cloud integration was a big factor of HP WebOS. It had an innovative multitasking card UI, so I recently learned that the iPhone X looks very much like what WebOS looked like back then. HP used a custom toolkit at first and later migrated to Qt 4.7, which is around the time that I joined the project. And recently, or not that recently actually, it was released open source as Open WebOS. And it was shipped, for example, on the Palm Pre, which is a smartphone with a keyboard, and the HP touchpad, which is a tablet. So LG acquired the WebOS IP, and so that was also the time that I joined, and we migrated to a new hardware platform, and we had new use cases and different input devices. So you can see the Magic Remote in the corner, which is a pointing device combined with a four-way arrow key navigation kind of ring, and a scrolling wheel, all of which the HP devices didn't have. They were all touch. And obviously, we wanted a new UX to fit all of these new use cases on the TV. So because touch doesn't make a lot of sense, and the TV is not a touchpad, designers invented a new UI to go with it. So, when we migrated the HP WebOS to our LG platform, we were left with components and had to find a way to connect them. So there's a compositor or window manager that we had. We started using Qt framework to replace some of the proprietary HP components that we couldn't take over or port. You have the system UI. You have a new hardware platform. You have things like apps, native apps, web apps, and the on-screen keyboard. And all of that we connected using Wayland. Now, Wayland was quite young at the time, but we found that it worked well and was stable enough for us to work with it. So we picked Wayland to connect all of these components. So the decision factors that went into our design is that the Compositor is just another UI, and as the UX evolved with new designs and changes here and there and different use cases being introduced, we wanted to stay flexible. So we used well-known tools to our team, which was QML and JavaScript, and that allowed us to handle application surfaces just like any other UI element in the scene graph. So we didn't have to learn much about that part. And at the time already, QtDeclarative and QtWayland already had good integration with each other. And so the decision was made. We would make a QtWayland compositor based on QtDeclarative and QtWayland, obviously. So our compositor is one process that incorporates both, or these 4 components being compositing surfaces with the live video plane. So live video is still on a hardware accelerated plane in the background, but surfaces are composited on top of that. This has reasons for image quality and well, memory bandwidth being 2 of them. If you have the video on a hardware plane, you can do much better image improvements on a specialized silicon. So window management is also another thing that we incorporated into our compositor process. So which window is in the foreground and at which position, and there's a C ordering if you have overlaid windows on top of each other. The launcher bar we also integrated because designs showed surfaces of applications that are currently running or have previously been used kind of weaved in and out of the ribbon that we have in the TV. So we decided the launcher should go into the same process. And it just came naturally that task switching also goes into the same process. And then we have a couple of Wayland extensions to fit special platform use cases now. XDG desktop was not the right fit for us, and so we decided to kind of implement our own shell. So this is a classic display server anatomy, as you might remember or recognize it from X11. So you have a compositor in the center, the centerpiece, which might be your X11 server, or in different configurations might be Western. You have a display protocol, which is X11 or Wayland. And you have processes that bind or talk that display protocol, like the window manager, or well, the applications in the first place, but then also the window manager and the system UI and home screen all talk the display protocol and connect to the compositor. The compositor just basically blending surfaces together. And then you have a system bus with different services that connect all of that. Now the WebOS compositor, instead we have everything that is window management and launcher and home screen is all in the compositor process. So it's all just QML. And QML uses Wayland through QtWayland QtDeclarative bindings. So all of the Wayland objects just show up as QtDeclarative items. And on the applications, we have QML or native applications. They use the QtWayland QPA, and web apps run on Chromium, on a Chromium runtime, which also uses the QtWayland QPA. What's happening? Yeah, and well, on the bottom end, our compositor process obviously has to talk to the screen or the hardware somehow. So we have our TV platform QPA, which is well, it's a kind of EGLFS kind of deal. The system service that we use on WebOS is Luna Service 2, which has been used on WebOS since before my time, actually. So if you want to implement or ship a Wayland device, you will have to have a GPU driver that supports a Wayland. And these are the pain points or the crucial points where you have to implement it. So let's start from the application side. The EGL driver or EGL user space library needs to be able to map a EGL surface that your application draws to a Wayland surface. The Wayland surface then you can send over the Wayland protocol. It's just a file descriptor at that point. And when the compositor receives it, it will need to unwrap that Wayland surface file descriptor and get a EGL image back. The EGL image then you can bind to a GL texture, and at that point you can just render it using OpenGL again. So when we started, Wayland was young, as I mentioned. So yeah, we didn't have Wayland support in our driver, and very few embedded GPU drivers did have Wayland support. We did prototype at that point, and libhybris, well, if I remember correctly, I think I actually implemented that part. So libhybris allows you to take the closed source GPU libraries, the user space part, it wraps it, and then you can call it on a glibc-based system. Like usually you don't have an Android. Android has a different C runtime, as you might know, and you might not want to use it. You might want to use the glibc. So libhybris wraps and loads these built for Android GPU drivers, and then you can use them in your GNU Linux distribution. Now let's look what it looks like from a code point of view inside the compositor. So I mentioned that the Wayland objects just look like QQuick items, right? So what does that actually look like? So here's a little example code snippet. What we did is the compositor exposes a surface model which implements the abstract item model, so it can be used in any view that you might want to use. And what we also have is what we call a window model, and it allows you to specify a filter function, a sort function. So, for example, you might want to filter surfaces that are full screen, like in this full screen filter function, and you might want to filter them by the last time it was full screen, so you can sort them in a kind of task switcher way. So this window model is also an abstract item model. And then at the bottom, we can just use that in a list view and bind a delegate to it. And in the delegate, we can just use the surface item, resize it to delegate itself and reparent it, and then we can just display it in a list. Now, there's a couple of caveats you must be careful about if you implement a QML compositor. So the scene graph renders your composition. What that means is that if you have a complex scene graph, the application's FPS or the rate that it can render at, it should match your display FPS of 60 Hertz most of the time. So if you have a complex scene graph, the compositor will bottleneck that, and you will end up having less FPS, and that's not nice to have. Your users will want to have fluid 60 FPS scrolling. So what we do is we minimize the scene graph when we put in full screen, so there's nothing else on the screen, just the bare minimum. For example, the app is full screen, nothing else on the screen. It should be just that surface being blitted using OpenGL, and then the user presses home and brings up the home screen, then that becomes visible again, and then the user is more focused on, he wants to use the home screen or launcher, whatever. Also, if you use QML to switch between surfaces, you should be careful with bindings that are too costly and that cause stalls, because that will be visible as glitches or stutter. So let's look at a couple of results that we achieved with this architecture. So obviously, I mentioned the TV. It doesn't animate, but it used to animate in the other file format. So We have the launcher ribbon, which I mentioned is part of the Compositor process at the bottom. We have a recently used app, which is ended up being just a snapshot, but it could, in theory, be live, actually displaying the application live. We have information about the foreground application, and then we have some buttons for quick settings. And in the background, we have the currently live application. Now, if that application ends up being a live input, like from tuner or HDMI or the other inputs, it will just be the compositor will just be transparent at that point, and we will see that optimized hardware video playing directly. But in later WebOS versions, we do support mapping TV input to textures so that we can actually move them around, rotate them arbitrarily. We also ported it to a smartwatch. So that was around 2015 early. So it scaled down to 240 by 240 pixels and a much weaker SoC. Obviously, it has a tiny battery, or has to have a tiny battery, so you use a smaller SoC and less RAM and so on. So we had to work on reducing memory footprint, CPU scaling, and still it should be fluid. And yeah, the watch has LTE connectivity, so it works without a phone. So power saving, memory saving, I mentioned. Input latency was a big issue because now when we ported to the watch, it was a long time since we last looked at the touch device. So this was the first time with the new Qt5 stack that we looked at touch again, and our previous use cases didn't include touch. So, and if you use touch to scroll, it becomes really noticeable if there's input latency, and you have to remember that the touch hits the scene graph of the compositor, then has to bubble into the item, the quick item that represents the application. The application has to process it. The application has to re-render itself to represent it actually has moved the list, and then that gets flipped, the surface gets flipped, and then bubbles up back to the compositor. At that point, the compositor will update the screen. So this chain of events needs to be optimized so that when you scroll, there's as little latency as possible. We also worked on reusability of components and modularization. So we had use cases of switching not only the watch clock face, which is an application on that platform, but also the launcher, which still was in the Compositor process. So we worked on unloading the QML, kind of tree from the launcher and downwards, and then loading a different implementation back. But we also worked to make the launcher itself a separate process, because in this design, it wasn't as integrated as on the TV. We also ported it to a fridge, which was more straightforward, but still a new UX design. We have a translucent touchscreen in a portrait configuration, and so this was I think, if I remember correctly, we were two-person effort, and in a couple of weeks we were able to port our existing and reuse our existing modules to a fridge, and yeah, so the fridge also shipped. Yeah, I was part of that team. And we also are working on signage solutions. So you might have seen in airports, there's many displays displaying current information, or in fast food restaurants and many places you have screens that show informations like timetables or the menu or something. And also hotels use our signage solution in different configurations. And the use cases we worked on here are linking multiple screens. For example, you can see that there's two TV screens side by side, and they show one scene graph. And we have different solutions for that we worked on. For example, GL call streaming, and also just HDMI splitting, and not sure that exactly works, but. So we have one solution using GL and one solution using just a raw HDMI signal, and also touch screens on these bigger devices. So some thoughts on QML and for our use cases. So QML allowed us to iterate on our designs quite quickly. And if you're careful with your components, you can make them reusable. And if you probably will have to have the odd native component just for performance reasons, but also to integrate with some service that you have on your system. Like in our Luna service, we have it's a native bus, so it has to have a native connection. So we have native items that we can then use in QML. The compositor is in the startup hot path, so it's the first thing that the user sees. You power on your TV, you want to interact with it, you want to use it, so the compositor has to come up quick. So you should watch out for time that the compositor or that a complex QML application will just take if you're not careful. So QML files have to be parsed, and then there's JavaScript in them that has to be compiled or loaded. And then there's you might have shader effects, or just the regular QML items use OpenGL to draw, so they use GLSL, and that has to be compiled. Now there are solutions for most of these. For example, Qt has now precompiled QML, and I think you can also, that also includes JavaScript, and then you can also use precompiled GLSL that gets stored with a hash, so the same file maps to the same compilation result. Yeah, these are things you can do. And you should avoid complex and deep scene graphs for the performance reasons that I mentioned earlier. You can also just lazy load things later just to bring up some message or something on the screen that the user can see, okay, my TV is it's doing something, or I can already do something, but once I press this menu button or that, it will lazy load some other QML in. 2 minutes, okay. So big images can store OpenGL in the text image 2D call, and that is, we found driver memory allocations, PVR, etc. are formats that use drastically less memory, so use them if the look of the image is not that important. I mean, it's like PNG versus JPEG. You need to know what is important at that point. The performance analyzer can point you to complex bindings and JS calls, and just use classic logging and tracing in places that you suspect. Yeah, so the Outlook is a application that we developed on top of our signage platform, which is a whiteboard that you can draw on. It has multi-touch. We plan to support pens and palm erase, and so you can erase with your whole hand. You can annotate over PDF files, and you can share files between participants. You can plug in your laptop and annotate on the HDMI output from your laptop. I would have loved to demo this, but while setting it up this morning, I let out the magic smoke from the LVDS HDMI converter board. So unfortunately, I can't demo it. And that is the end of my presentation. Thank you.
Yeah, what a pity
Yeah.
you don't have that with us.
Well, I can show you the hardware, but it's dead.
Are we not interested in hardware at all? Are there any questions towards Florian on I would say, pretty ambitious setup you have? Happy Qt use? So any questions on your end? If not, then we just continue with the next speaker. Thank you very much.
Thank you.